Hello and welcome everyone to today's session, Battery Energy Storage System Safety and How to Avoid the Worst Case Scenario. It's actually the first webinar of this year, so I'm very happy to welcome everyone here. We are seeing a lot of interest in the topic, in the sign-up figures, also with so many of you that have already joined. And that's, of course, because this is becoming a bigger and bigger topic with energy storage systems now being used to stabilize grids, reduce the electricity bill, or just provide grid power. No one wants to see that storage failing or, in worst case, even being on fire. We will take a closer look today into what's causing that and how you can prevent that. With me today are some great experts on the topic. So you can expect some real deep insights. And we'll do a quick round of introduction to start with. But first, let's do some housekeeping. So we want to keep this webinar as interactive as possible. So please make active use of the questions tab. We will address all questions, if we have time, at the end of the webinar. You should find this tab at the bottom of your screen, and you can just type a question there. You cannot leverage the chat function in this case, but feel free to reach out to us afterwards or use the chat with the organizers in terms of any technical difficulties. So today with me are Matthias, Jan, Ryan, and I would just hand over to Matthias first for a quick introduction of himself.
Yeah, hi everyone, I'm Matthias. I'm part of solution engineering at TWAICE. So sitting somewhere in between our sales colleague and the tech product departments. Have a battery background, very much looking forward to our discussions or what we have to talk about today.
Gonna take over. Hi, I'm Jan, product manager of the energy team. Looking forward to your feedback to really build products you need and addressing your problems. Thanks, looking forward.
And that brings it to me. So good afternoon, good evening, good morning, everybody. My name is Ryan Franks. Similar to Matthias, I am in solution engineering. I've been in the battery and energy storage field for about 14 years, primarily dealing with safety, testing, and techno-economic analysis. Leonard?
Well, thanks everyone there. My name is Leonard Hinrichs. I'm VP of Marketing, Partnerships, and Industry Strategy at TWAICE, and I will be the host tonight. So what can you expect? Well, first of all, a brief introduction from my side on what TWAICE does. I will take the liberty on doing that, and then we'll have Ryan talk a bit more about why safety is a relevant topic, Matthias going more into the technical causes of safety, and Jan is then presenting our solution and answers to that. And of course, all three will be answering your questions. So we at TWAICE take this topic of batteries very seriously, and it's about eliminating the risks of safety. So this is where, the risks of batteries. So this is where safety comes in, but that also extends to topics like warranty and health. We work with customers on the mobility side, both in the M space, as well as there's a problem with my connection. Interesting. Right. So continuing on that, eliminating risks, apparently also eliminating the risk of just losing connection. I'm afraid nothing to be done about that. It's a live show. Sorry for the little hiccup. So I was just talking about our customer base, and we're looking both at OEMs, mobility operators as well, but today is primarily focused on our energy customers and what we can deliver in the energy industry. And I would also just leave it there and then hand over to the topic of why safety and let Matthias shed some light on that.
Talking about the importance of safety, you can go ahead and click through to display the next graph too, Leonard. Thank you. So the concept of energy storage safety comes up in the news with increasing frequency. And the importance of it is that these do happen intermittently, but they are fairly high impact events. And the consequences can be quite severe. There can be the potential for a loss of life, property, injury. but more so if there's not a truly catastrophic event. There's a lost revenue opportunity, certainly if the system is taken off of line, as well as bad indirect effects, bad public relations, investor relations, etc. And the problem with the analysis of safety is that it's a holistic concept, but we have to truly get into the root causes and determine what to do about it. On the right here, you can see a graph of energy storage system incidents per year since 2016. And this will only continue to promulgate throughout the years, as well as I would foresee increase in frequency as more energy storage systems come online, just as a matter of the law of numbers. But you can see that it's not limited to any specific battery manufacturer. It's not limited to any specific geographic area, and it occurs in Europe, in the Asian countries, and in the US and North America as well. So if in talking about recent trends and events, one of the trends that is occurring is that energy storage systems are increasingly being deployed in more diverse environments. One of those environments happens to be urban situations. There are, for example, a number of systems that are going into New York City. And here you can see an article on the concerns of energy storage systems being implemented onto a rooftop in New York City. On the left, this is a screenshot taken from the EPRI battery and energy storage incident database. And what I've circled here is just the incidents that have occurred in the last 2 months from this time period. So the result is clear that this is a problem, yet energy storage system safety is an issue that is not going away, and it is something that has to be diligently planned for in the design as well as the operation of systems. And if you could click through to the bullet points there, Leonard. One of the other trends that is occurring is that, as many people in this audience will likely be aware, there are increasing regulations. So one of these topics is energy storage codes and standards that affect the entire energy storage system. In terms of fire safety, these are things like the IFC or the International Fire Code, as well as one of the best practices is NFPA or National Fire Protection Association 855, the standard for the safe installation of energy storage. There's also system standards that differ from the codes and the codes reference, like UL standards 9540 and 9540A for fire testing in the US. But also internationally, there is a growing body of safety standards, including the standards that are under the IEC 62933, which is the body of work under Technical Committee 120 at the IEC, which will be referenced and promulgated in countries that typically reference and promulgate IEC standards. But most interesting, perhaps, for what we're talking about in terms of battery analytics is component standards. There's an increasing body of knowledge in IEEE P6286 and IEEE's P2686 and 2688, respectively, for battery management systems, BMS, and energy storage management systems, ESMS, that are coming into fruition that do reference the ability to convey data, to make accurate decisions. And so all of this, the directionality is clear that battery analytics will play an important role in the active safety of systems. This is a shot from what I would consider probably the best body of knowledge in terms of thinking philosophically about energy storage system safety. This is called a bow tie diagram. And on the left, you can see threats, threat barriers that all lead to a hazard scenario. And then there are consequence barriers and consequences. So a simple example going from left to right might be an internal cell failure of some type, perhaps a cell manufacturing error or something of the like. A threat barrier would be something like a disconnect switch that might isolate that. The hazard, if that doesn't occur, would be something like a fire, put simply. A consequence barrier would be something like a fire suppression system, and a consequence would be a fire. Now, the hazard scenarios really are pretty short in their list, including cell internal failure, thermal risk. You can have controls failures, electrical risk, and environmental risk. We've changed the slide here, I suppose, but yes. But the point to convey here is that what we are addressing at TWAICE, the TWAICE and battery analytics, can serve as an advanced threat barrier to prevent a threat from ever promulgating into a hazard scenario. In summary, the importance of this proactive safety, of recognizing when an event may occur, getting notifications, and what we're going to talk about, can really have true impacts on time, money, and public relations. There can be environmental mitigation costs. You can face higher project costs in the future if there's an incident. And purely, there can be unnecessary staff time and attention and labor costs. But there's real effects on communities here. Just in the past 2 years or so, here's 2 examples of a battery fire, Standish, Michigan. There was a energy storage incident that produced gassing that closed down, affected a neighborhood. There were shelter-in-place notifications, closed roads, and perhaps better in the news, Moss Landing, of course, last year, experienced one of a few fires that it has had. Again, there was shelter-in-place warnings, as well as a major highway, Highway 1, running down the coast of California, that was closed temporarily because of this incident. So to get to these real concerns, I'll turn it over to Matthias, where he can address some of the causes of these energy storage system incidents. Matthias?
Yeah, cool. Thank you, Ryan. Yeah, so as we've seen before in the slides of Ryan, we're going to look a bit more into the hazards. And at the end, it kind of makes sense as well to try to understand what the underlying issue is, right? So to kind of be aware of the true problems, which are at the end leading to these events, because kind of only if you understand the underlying issues, you can as well tackle the problem, you can prevent these incidents. And if you cannot prevent them, at least you can be prepared and as well at the lookout for them. And so let's focus on the most relevant one, right? So that should bring us already quite far. So what is actually the most common cause for a battery fire event? Happy to kind of take any suggestions. And I was honestly very surprised when I read that result while doing that research. It's actually the unknown, the cause unknown. Somehow as well spooky to a certain extent, because that I think makes as well the true, or just shows how challenging that topic it is as well. But at the end, it as well just makes sense if you think about it. A lot of times when you have these severe safety incidents, your storage, and at the end as well, your batteries are completely damaged afterwards. So making a post-mortem investigation, so looking into the ashes of your storage and trying to understand what really caused all of this is just impossible, or at least challenging. And so there are a lot of investigations as well ongoing of well-known companies trying to understand really what happened in these causes of these battery fires. But then often you just end up having different or even conflicting finding from these different or multiple parties. So that's as well just a challenge here. And but nevertheless, we can kind of think the other way around, and that's what we want to do now. So not from the ashes back in time to the battery, but rather from the battery into the future and how to avoid these ashes. And so first focus we want to put now is on the battery-related causes for safety events, so aka fire. So the causes for which the battery itself is, or at least can be made responsible. And so if you click once, yeah, here we go. First off is, because it is as well the earliest point in time of a battery lifetime, the manufacturing issues. And one of the more famous examples of that issue is probably the electric vehicle from GM, the Bolt. And here the issue was, for example, a torn anode tab and folded separators, which at the end caused battery fires in a handful of cases. And so at the end, these manufacturing defects, which underlying reasons there might be, generally you end up in a process in which kind of both electrodes in the battery are connected, and you kind of create an internal electric conductive path there. So something like an internal short circuit. And if that kind of path is stable enough to carry as well larger currents, you just heat up the battery and you kind of trigger a thermal runaway. And that kind of causes the entire problems. And so kind of that fire symbol we have there in the middle, usually the thermal runaway event, at the end just creates more and more heat by reactions happening inside of the battery. And then these reactions just trigger further reactions and lead to even higher temperature. And you kind of have that vicious circle going on. And what really happens as well inside is as well just decomposition of your electrolyte, your solid electrolyte interface on the anode side. And then even that goes further, you kind of have a decomposition of your anode, usually your graphite-based anode. And then same here, more and more reactions. You can keep on heating up the battery. And then at one point you as well decompose the cathode side. And then same goes on. You have more reactions happening. You generate more heat. And that's that kind of last stage. For some chemistries, you reach temperatures above 1000 degrees Celsius. That's super hot. And kind of to put that as well in the perspective, usually aluminum starts melting around 660 degrees Celsius and copper somewhere around 1100 degrees Celsius. So it gets really hot. That's as well always the problem around that. And because we already talked about different cell and cell chemistries, one side note there, because we kind of as well, if you talk about safety, that usually as well always comes up. Nickel-based chemistries are usually more reactive and hence create as well higher temperatures. So that's kind of the higher than 1000 degrees Celsius. That's what you do with nickel-based cell chemistry. And in contrast to that, you might have heard that LFP is supposed to be the safe chemistry, but as well LFP can go into a thermal runaway. It gets less warm, but at the end, same problem. And so cell chemistry improvements itself will not solve the safety problem. And that's as well why we need kind of as well analytics to tackle that. And so we already see one of these other conditions there. So there are different abuse conditions which can trigger otherwise as well a thermal runaway, the electric, thermal, and mechanical. And so from an electric viewpoint, you can either have an external short circuit because you connect the two terminals of the battery directly with each other, or because you overcharge or over-discharge your battery. So short circuiting is just like a very high, fast discharge, and you just create a lot of heat, and then cycle goes on and on. And with the overcharge and over-discharge, at the end, it leads to side reactions in your battery, electrolyte decomposition, copper dissolution, and then you create an internal short circuit. Then you can click once more. Then we come to the thermal abuse. So it's similar to a thermal runaway, but you trigger it by the temperature itself. If the temperatures are just high enough, the material inside the battery can just already start decomposing, and then cycle continues. We create more reactions, generate more heat, and then you are in that kind of reinforcing cycle. And then lastly, in that first section, we have the mechanical damage as well. So at the end, it's a bit of a mix of the others, but it's initiated by a mechanical shock, for example, like a hit on the battery, or the battery falling, for example, on the ground as well, or constant pressure onto the battery housing, which at the end can cause an internal short circuit, similar to the manufacturing defect, or for example as well, you start creating lithium plating, you have your internal short circuit, and then you have your safety incident. And so understanding all of these kind of direct causes brings already a lot of value, and just as well understanding and know where they come from increases the safety of your battery already significantly. And so if you click once more, we can call that kind of inner space as well, the inner circle of risk, or inner circle for safety. But of course, that's as well not everything, especially what Ryan as well talked about at the beginning. A safety event happens not because of the battery itself. There's as well a lot of stuff around the battery which can fail. And then let's look into that as well. So causes from a non-battery related topics and the components and so on. If you read the news, for example, you find an example of a cooling system, or the HVAC as one cause. So at the end, just your system, your HVAC system broke, or it was not performing as it was supposed to. And so then you just slowly increase cell aging. And then with that, of course, as well comes later a potential safety incident as well. If you click once more, another example from the news are kind of other components in the system next to the battery maybe started creating smoke, smoke, which at the end triggered a sprinkler system, which at the end is kind of the benefit or what planned, or it performed as it was supposed to be. But of course, with batteries and water, that just doesn't work too well. You ended up creating a short circuit with the battery cells, and then went into thermal runaway, and you kind of know the story then. And then if you click once more, something less often seen, but as well already observed in some examples, are cable fires. So the cable itself might be damaged due to mechanical stress, overheat, and then at the end starts a fire. We have it as well, the example that in inverters, you can observe that simply bending the cables too much can create already a lot of heat, and then you kind of damage the cables. In case they are kind of very tightly packed as well, you just create a lot of more heat, which at the end might as well ignite a fire, and then you all kind of have your incident coming up. And then last category are as well, just if you click once more, Leonard, accidents or even just catastrophic events such as building or infrastructure damages, wildfires. That's kind of that category. And kind of lastly, if you click once more, we still have the, so to say, the unknown. But I think as well, just from a strategic, theoretical, and kind of experience-based viewpoint, we kind of have that as well largely covered. So if you click once more, that's kind of happening in the, let's call it, outer circle of risk, because it's not directly linked to the batteries itself. So I think that's as well just something we're all battery enthusiasts, but we need to be honest as well and admit that a fire in which a battery is involved becomes always more complicated, not more severe. I think that's as well important to understand, but at least more complicated as well to handle for the firefighters which are involved there. And hence, we need to make sure that not only the battery itself is covered and monitored, so kind of the inner circle of risk, but also to a large part the outer circle of risk. And that's of course what you can't control everything. That's just as well understandable, and that's also why you have fire suppression systems at the end. But it should as well be taken into account. And so coming to our kind of approach, these kind of two circles, you still remember the outer and inner circle of risk, and the safety solution at the end should cover just both of them. And so you kind of build two lines of defense against these two circles you have seen, to these kind of different risk spaces. And that's kind of the idea here. So it really gives a holistic view on the system, not only the battery itself, but it needs to kind of take the surrounding components, the periphery into account, because that's as well underlying issues which just can create a safety event. Cool. And then my last slide here, we talked a lot about safety for systems once they're in operation. So that's the inner and outer circle of risk during the in-life phase, if you click once more. But it's as well important to understand that true safety considerations, of course, start as well long before the system goes into operation. And so it's as well the design or the development phase, which also kind of determines your safety and the risk as well at the end. And so how do you actually kind of design a system which is safe? I think that's as well just challenging. We discussed before all the different causes, and you need to take them all into account as well already in your design phase. So a lot of topics to cover, different kind of mechanisms to consider. And so for the inner circle of risk, you kind of need to set the right operations limits and select as well the right cell, understand how that cell will behave throughout its lifetime, but also at the end, influence from the surroundings should be considered. So, for example, the temperature distributions within a system and all of that. And so I think that is why a crucial point to understand that we can tackle a lot of problems with battery analytics, but you can prevent as well some of these already, at least by the right tools in your development phase. That would be it for me now, and then I would hand it over to Jan.
Thank you very much, Matthias. I will give a quick overview of our product, jumping in on setting the stage here. What do we want to achieve here? How do we make your batteries operation more safe? Think of us as a second safety layer of your BAS in the cloud, really making sure we detect and predict incidents before they happen, best case months and weeks ahead, so your O&M team can react appropriately. If you click on more, we go into detail how we do this. First of all, you get alerts, active alerting on any kind of abuse, could be electrical, could be thermal. Second, we are tracking, continuously monitoring trends, which might be self-relevant because not every event does happen overnight. You can see, for example, spreads or the DC resistance growing in some parts of the BS over time, and we keep you informed about that. But also we look at electrochemical topics like the detection of lithium plating, which can lead to dendrite growth. And at the end, we provide all the data necessary to your teams and the tools to obtain a root cause analysis and make sure the problem is mitigated. If you look at the right-hand side, just to make sure we're not a replacement for any edge sensors or a fire suppression system, this is still needed. We're just way ahead of these systems, trying to give you a better status quo if something is happening. Next slide, please. Before we jump into a deep dive in our product and some examples, I want to quickly get everybody on the same page here, how we categorize different safety incidents from inner circle and outer circle, as Matthias explained. Here, I start with the BMS. BMS really has one purpose: make my operation safe. And usually this is really by making sure none of the cells is exceeding voltage, current, temperature boundaries. But we also know reality is sometimes not predictable, and we can see BMSs leading to overcharge, deep discharge, abusing the single batteries. And also the limitation in historic data of these BMSs limits its ability to detect trends, to do anomaly detection, as well as the limited compute power just lets really barriers the options of doing analytics on edge. And that's why we think the cloud solution here is a good idea. Next, please. I will elaborate on that later, but thermal monitoring is another category, really making sure you don't exceed any thermal events. The spreads, the temperature spreads are not too high. Electrochemical, I start with that. This is really about the battery system as a whole, really making sure the chemistry in there, the chemical processes are all fine. For example, I pointed out the lithium plating detection, which can lead to dendrites and then lead to a short circuit as well. And on the right-hand side, you see sensor drift. This is just to make sure we really see all the data and receive all the data your BAS is providing us, and that we don't have false information here. Okay, next slide, please. Let's take a look at our solution here. On the right-hand side, you can see the screen for the incident summary. Basically, this is the event your operation team would receive. We will go into details here later. What we can detect, just the clusters, is this thermal monitoring. Yeah, next, please. Where we can, so for all the battery engineers among the audience, this would be the deep dive now. On temperature, we can detect thresholds, upper and lower limits. That's pretty simple. But we can also detect the temperature spreads, which the longer your system operates, the more aging it experiences, and the more important the temperature spreads is to really make sure HVAC system can cover that. And that's also one monitor. When we have data, for example, or data access to the van, we can control and check if the HVAC system correlates with the temperature. On the electrochemical monitoring, we have a sophisticated weak cell identification by using the location and the voltage spreads to really identify are there malfunctioning cells which come from production errors. In the similar realm is the DC resistance. As said, for lithium plating, we use a stripping plateau detection algorithm to really make sure we summarize all these events when lithium plating takes place and warn you ahead of times. I already went through the BMS monitoring in detail. Here also we take care that the balancing is effective on your cells, and a sensor monitoring, as said, does also do this validity check if we have any drifts in sensor. If the data we receive and the analytics we perform on that is a ground truth, is really good working. Next slide, please. Let's take a look at one example incident, how this could look like. From top to bottom on the right, you can see the 4 monitors I explained in detail. You get more information on the incident, what happened, when happened, which component was affected. Then you get this lifetime graph of the solution, seeing this component compared to other components. Here we can see a temperature rise at the end, which triggered this alarm. But looking at the lifetime, we can see this is not an incident happening overnight. We already had a long time of temperature spread and also temperature anomaly. You can see at the bottom layer the component history. So your team gets all the information, not just for this incident, but over the whole lifetime to get a better picture what this component experienced in the past. And then the next one would be to just move into the Data Explorer and then, for example, correlate this temperature events with the HVAC system data to make sure this is not the root cause why this temperature rise occurred. This is just one example. On the next slide, I'll give you another one. We also do forensic analysis, so post-incident. So if you already had your storage burning or having severe incidents, we help you to analyze with the data what is the root cause of this issue and can we identify countermeasures to prevent this in the future. For that, we run the same safety algorithms as for the real-time solution, but on your historic data. Instead of giving you a product here, we provide you with reports, really summarizing all the nitty-gritty details we find in your system. On the right-hand side, you can see an example where we could identify with our weak cell identification and the DCR, that as DCR, DC resistance, that we have a few cells in some components really being off, having or having manufacturing problems. And we could also identify the cell, which is the round bubble up there, which then led to a thermal runaway. If you click next, to summarize here once more, we do detect safety incidents continuously, which also lead to replacement either of modules or of sensors to keep these devices from our customers safe. We do forensic analysis as a post-mortem solution. So you can also check if we would be able to detect future incidents for you. And we also move over to regularly do some sanity safety checks in our commissioning report. So if you start your operation and you're in commissioning, we make sure the system you receive as an asset owner is in safe space, and as an integrator that you have built a safe system. Last, I want to end with a quick comparison here of the cost of the battery system compared to the cost of safety monitoring. And as you know, most of the time, this is not a big issue, but if an incident happens, the consequences are severe. That's it from my side. Looking forward to answer your questions, and back to Matthias.
Well, I think
Yeah, no problem. Yeah, so in the past half an hour or so, we've covered why energy storage system safety is important, what the causes are, and now what part of the remedy to those problems is. And so we would really encourage you to talk with us or get in contact with us if you have a couple of different use cases. So first, if you're planning to start an energy storage system soon, many of these incidents do occur within the first year of operation. Check out our commissioning reports. If you have any doubts about the status of your system, please connect it to the TWAICE platform, and we can be able to work with that data and derive insights from it. If you've had an incident, we can do an analysis on that. You can share your data with us, and we can be able to help you determine things like subrogation in terms of insurance, root cause analysis, etc. And finally, if you just want to learn more, we get challenges all the time. People come to TWAICE and they say, here is an incident, or here is an anomaly that we've had. What do you think? Can you look at this data and help us determine what is going on and make sense of it? So finally, battery analytics, the one thing working with it has really taught me is that it is one thing to have available ESS data, but it is an entirely different thing to be able to visualize that data and be able to derive any sort of meaningful insights out of it. So we'd really encourage you to go to TWAICE.com or contact us at sales@twice.com in order to de-risk your batteries, outperform your competitors, and use battery analytics. And so now I think we'll go into questions, right, Leonard?
correct. Yeah, thank you everyone around. I think that was very insightful indeed, and I can see that there are a lot of questions coming in, and Matthias has been busy in answering some, but I think it makes sense to discuss this as well. Maybe starting with something on the data. So that is whether we measure voltage, current, and power of each single battery cell. And I think this is a question to Jan or Matthias, I guess.
At the end, we don't measure the voltage or the current of each cell, and we don't measure this stuff by ourselves. So we get access to the BMS data or SCADA systems or whatsoever. But at the end, we receive the data sets. Usually you get like minimum or maximum cell voltage, and then usually as well the ID or the location of that kind of cell, which shows the minimum or maximum cell voltage. And then that kind of information you use to kind of pinpoint the kind of interesting cells or the weakest cells or the worst cells from a kind of safety perspective.
Cool. Then we have a question, I think that is also from Jan, your presentation on a feature that is called stripping plateau detection, and whether we could elaborate on that.
I think this is, to be honest, this is an NDA concerning topic. So I think if we're further on in the process, having signed an NDA, I can go into details here. But certainly you can check the internet. There are multiple models for that. I don't want to go into detail on public. Yeah, sorry, weak cell identification. What does this mean? So what we combine here basically is the voltage spread among all the cells in a module. If we have this data, sometimes we only have, as said, min max voltage on that level, and we correlate with the location and add some magic sauce on top. We can see if these cells are popping up more and more frequently as a limitator. seen in the max cell and min cell voltage, we can identify then that this is the weak spot of this pack. If that answers that question.
Very good. Then we have another one that is a bit on the prediction and how many days or hours in advance can you reach the prediction, or when do you know about a thermal runaway? Would be posing that.
I would take that as well.
Very good.
Matthias, feel free to jump in. So this is a tricky one because it really depends on. We can see trends early on. The question is, when should we warn you? What we can't predict is in 6 weeks, 6 hours, and 35 seconds, we will have a thermal runaway on the system. But we can set with the customer and our experience some crucial thresholds based on the chemistry, based off the model type, and the experience we had in the past with these storages to really make sure we warn you ahead of time. Usually this is in the weeks ahead, sometimes months ahead, but not minutes.
I think that's the important part. Prediction time, you have time to react in that case. And we have seen a couple of questions here surrounding cell chemistry and the differences it makes, I guess, in particular regarding NMC and LFP. Matthias, since you already went ahead answering it, maybe you can also elaborate here in this forum.
Yeah. I mean, so as mentioned during the presentation as well, no matter which chemistry you're looking at, it can go into a thermal runaway. At the end, which kind of temperatures and heat you will experience is going to be different, and potentially as well what kind of gases you're going to create from a kind of toxic point of view. That's going to be different to a certain extent, but at the end, as well said, just by improving cell chemistries, we're not going to end up with completely safe or risk-free batteries. We're going to have some analytics on it to kind of keep them in a safe state. And it's at the end as well why we're here.
Very good. Then we have a question regarding the inner circle defects, the manufacturing. So as we cannot rule out manufacturing defects completely, so is TWAICE working on some battery fingerprints in quotation marks to avoid such scenarios?
I'm just going to try to answer it in as far as I understood. So at the end, you kind of have a fingerprint for each battery because you usually have 1,000 of these in your system. But at the end, you have as well, and that kind of gives you as well the possibility to compare thousands of cells against each other. So you kind of have as well a way to detect anomalies with a very large data set. Nevertheless, as well, just from a kind of modeling or theoretical viewpoint, you can as well derive the kind of behavior which the battery is supposed to show in case something is wrong from the beginning on, and then that's kind of what you're kind of at the lookout for. So that's kind of the faulty fingerprint we kind of look out for. So there are ways to do that, but at the end you as well leverage statistics to in addition to that.
Very good. And what stakeholder is mostly using these services?
Yeah, I'll jump in here. So there's the problem with energy storage systems is that there is not really one defined business model. We've sort of seen this progression over the last 10 years from a battery OEM providing a backstop to a full wrap EPC, electrical procurement and construction firm, to now more of a commingled environment. But we have and continue to work with a number of stakeholders on the utility side, obviously utilities, but in addition, asset management firms, insurance companies, project developers, owners and operators, and communication firms, as well as integrators at times.
Very good. And then I have one more here on what would you consider to be the top 3 highest safety risks with current battery energy storage systems?
Yeah, I can go ahead and start, and Jan, if you want to add in. So I think that what things boil down to is, I mean, I really would point to three. I mean, the first is, as somebody remarked in the questions, even if you have excellent quality control over your battery production, even if you have multiple sigma quality control, you're producing so many batteries that you are going to end up with some that have defects at times. The second is in the controls and set points of batteries, simply because people, this has kind of been the case in South Korea in a lot of the 2018 fires, where systems were pushed beyond their operating capacity in terms of just control algorithms in order to make revenue, and that can be a problem. And then the third, I would say, is simply incorrect design. And this is going to widely vary, but things like inadequate HVAC, breakdowns, Jan mentioned, the folding. I think Jan mentioned the folding of cables, incorrect bus bar sizing, and simply those sort of holistic system issues that kind of bubble up from the components to the whole top level system.
May I one more thing here, just from product manager perspective. The problem is most of these projects are built project by project, not modularized. So even if the battery is working fine, if you take a look at the Moss Landing incident, where cascading effects of a leakage in the sprinkler system leads to with the wrong firmware of a sensor, leads to a gasoning, and then really incepting a fire. So these rolling incidents with cascading effects, they can be so complex, they can be of diverse origin. So at the moment, it's just too early to really pinpoint at certain failures which occur more often.
Right, cool. I mean, and going on to that question coming here in on the topic whether you believe, and I would put that to Matthias, sodium ion or solid state batteries could be part or one of the solutions to safety issues.
That's a twofold answer, I guess. So solid state, I don't think so, because as well that can at the end create just as well a thermal runaway, and you have the same problems ending up there. Sodium ion potentially is just as well from the chemistries you use safer. At the end, we say that as well about LFP. I'm sure with sodium ion batteries in the field, we're going to have as well safety incidents happening, because that's all the outer circle of risk is all about that. Because it's not only the battery, it's as well the entire system you need to have under control. So you kind of get rid of one of these causes if you kind of go to a more secure or safe chemistry, but it only brings you one step closer to true safety.
All right, and I think then there were two questions on second life batteries. Well, obviously the topic of safety is becoming even more important, and there's the question whether that is a difference to first life batteries, what the difference is, and more particular the question about BMS specific issues.
In general, there's not a big difference when you usually look at the incidents happening. They happen within the first couple of months or years even. So you kind of often have the problem from the beginning on of the system going live, which might be a manufacturing defect of the battery, but as well, maybe as Ryan mentioned, is an incorrect design of the entire system. So no matter if you do it with a first life or a second life battery, that problem exists. With second life batteries, what the main problem is probably going to be that you have inhomogeneities in your system, and meaning your BMS is going to have to make a very good job in balancing these. If it doesn't, then you just increase these inhomogeneities. You put a lot of stress on the weakest or the worst cell again, and then you kind of have the same problems again. So it's a bit difficult to say what the BMS is supposed to do. At the end, it's supposed to do its job, but we just as well see from reality that it doesn't do that all the time. So making maybe monitoring for second life even more important. But from kind of a general viewpoint, there shouldn't be a big difference.
May I add one use case for second life, which we hear from insurance more over the S3 point, they call it. So the accelerated aging point, to really be sure to detect that and then be able to replace it. That becomes in second life batteries more important than first life. So when this linear aging gets accelerated, this tipping point is crucial for safety and should be monitored by the BMS.
All right. And then we have two questions actually related to the operations. One is whether this can also be used to reduce operational costs. And the other one is more related to how well it can be implemented and also whether it can be tied to shutting down the storage automatically.
Yeah. So the operational cost is an interesting angle for sure. Looking at operations budgets for energy storage systems, probably the costliest thing is rolling a truck. So in combination with the safety monitoring, alerting in advance and being able to determine when maintenance should be scheduled or any sort of prevention of sending a crew out to restart a system or repair something can save enormous amounts of money. Yeah, this is a common distinction that's important to get, is that this TWAICE, what we're doing with battery analytics is not intended to be that direct tie to a fire suppression system, that direct tie to an inert gas deluge, or something of that nature. Rather, it's intended to be able to look into the future, as Jan was describing, and be able to determine in this window in the future, this is a trend that has been observed. This is an anomaly that has been observed. Take action in how you run your operations, or pay attention to this area or operation of the energy storage system. But no, it is not a pull the fire alarm type of situation. We hope, and frankly, it's much better to not do that, right? It's much better to avoid those incidents altogether.
I think the last question was on integration. Happy to go on the details here. We offer a email support, but also we do have a notification API where we can integrate that into your O&M preferred tool. Happy to discuss that in a sales call, for example.
Yeah, and I hope we answered all the questions, went through it, was quite a lot today. So thank you very much, everyone, for being such an active participant. Thanks for tuning in. Everyone will receive a recording of this webinar as well in their inbox afterwards. We are very happy to engage in further discussions, providing more details also on the topics that we cannot talk about on public display, but we could do it in an NDA conversation. So please make vivid use of our personal email addresses or the sales@twaice.com, or just go through our website at twaice.com to schedule a call with Matthias, Ryan, or Jan. Thanks for tuning in. Thanks, guys, for presenting such an important and interesting topic. If someone of you is tuning in from the US, we'll also be at the Energy Storage North America the week after next week. So also come by our booth in that case. Thanks, and bye-bye, everyone.